Welcome to our exploration of numbers between 1 and 1 million. Today we're diving into a fascinating mathematical question. How many numbers in this range are neither perfect squares nor perfect cubes? We'll break down the concepts, use logical reasoning, and discover an efficient approach to solve this problem. Let's start by understanding what perfect squares and perfect cubes are, and why they matter in this context. Perfect square is a number that can be expressed as the product of an integer with itself. For example, 4 is a perfect square because it's 2 times 2, and 9 is a perfect square because it's 3 times 3. In our range from 1 to 1 million, we'll need to count how many numbers fit this definition. Understanding perfect squares is the first step in solving our problem. Perfect cube is a number that can be written as an integer multiplied by itself twice more. For example, 8 is a perfect cube because it's 2 times 2 times 2, and 27 is a perfect cube because it's 3 times 3 times 3. We'll also need to count how many perfect cubes exist between 1 and 1 million. This will help us identify numbers that are either squares or cubes. Let's count the perfect squares in our range. The smallest perfect square is 1 and the largest is 1 million, which is 1,000 squared. That means there are 1,000 perfect squares between 1 and 1 million. We'll use this count later to help determine how many numbers are neither squares nor cubes. Now let's count the perfect cubes. The smallest perfect cube is 1 and the largest is 1 million, which is 100 cubed. So there are 100 perfect cubes between 1 and 1 million. This count is crucial for our calculation as we need to know how many numbers are cubes to avoid double counting. Some numbers are both perfect squares and perfect cubes. These are called perfect sixth powers because they can be written as an integer raised to the sixth power. For example, 64 is both a square 8 squared and a cube 4 cubed, and it's also 2 raised to the sixth power. Let's count how many sixth powers exist between 1 and 1 million. Find the number of sixth powers. We look for numbers of the form n6 where n is an integer. The smallest is 1 6 equals 1 and the largest is 10 6 equals 1 million, so n can be any integer from 1 to 10. That means there are 10 sixth powers in our range. These numbers are counted as both squares and cubes, so we need to account for them to avoid double counting. To find the total number of numbers that are either perfect squares or perfect cubes, we use the principle of inclusion-exclusion. This principle helps us avoid double counting numbers that are both squares and cubes. We add the number of squares and cubes, then subtract the number of sixth powers. Let's apply the principle. There are 1,000 perfect squares, 100 perfect cubes, and 10 sixth powers. So the total number of numbers that are either squares or cubes is 1,000 plus 110 equals 1,090. This gives us the count of numbers that are squares, cubes, or both. Now to find how many numbers are neither squares nor cubes, we subtract the total we just found from the total number of numbers in our range. There are 1 million numbers from 1 to 1 million. So 1,001,090 equals 998,910 numbers are neither perfect squares nor perfect cubes. Let's recap our approach. We counted the perfect squares, perfect cubes, and sixth powers in the range. Using the principle of inclusion-exclusion, we found the total number of numbers that are squares or cubes. Finally, we subtracted this from the total to get the count of numbers that are neither squares nor cubes. Understanding how to count numbers that are neither squares nor cubes is more than just a math exercise. It's a great example of logical reasoning and efficient problem solving. This approach can be used in many areas of mathematics and computer science, especially when dealing with large data sets or complex counting problems. The method we used can be generalized to other ranges and other powers. For example, you could ask how many numbers are neither squares, cubes, nor fourth powers in a different range. The principle of inclusion-exclusion is a powerful tool for these types of questions. Let's visualize perfect squares. Imagine a grid where each side has the same number of units. The area of the grid represents a perfect square. This helps us see why squares are so special in mathematics and why their count is easy to determine. Now picture a cube where each side has the same length. The volume of the cube is a perfect cube. This visualization makes it easier to understand the concept of cubes and why their count is based on the cube root of the largest number in our range. Sixth powers are rare in our range, but they play an important role in our calculation. They represent the overlap between squares and cubes. By counting them, we ensure our answer is accurate and avoid double counting. The approach we used is efficient because it avoids checking each number individually. Instead, we use mathematical formulas and logical reasoning to quickly find the counts we need. This saves time and is especially useful for large ranges like 1 to 1 million. Mathematical reasoning is key to solving problems like this. By breaking the problem into smaller parts and using logical steps, we can find the answer quickly and accurately. This skill is valuable in many areas of life and learning. Counting numbers that are neither squares nor cubes has practical applications in coding, data analysis, and mathematical research. For example, algorithms often need to exclude certain types of numbers, and knowing how to count them efficiently is important. You can extend this approach to other powers such as fourth powers or fifth powers. The principle remains the same: count each type, find overlaps, and use inclusion-exclusion to get the final answer. This flexibility makes the method very powerful. In computer science, this problem can be solved with an algorithm that calculates the counts based on square roots, cube roots, and sixth roots. This avoids looping through all numbers and makes the solution scalable for even larger ranges. Double counting is a common pitfall in counting problems. By identifying overlaps such as sixth powers and subtracting them, we ensure our answer is correct. This careful accounting is essential in mathematics. Let's check our calculation step by step. We counted 1,000 squares, 100 cubes, and 10 sixth powers. Using inclusion-exclusion, we found 1,090 numbers that are squares or cubes. Subtracting from 1 million gives us 998,910 numbers that are neither. A visual summary can help us understand the process. Imagine 3 circles, one for squares, one for cubes, and their overlap for sixth powers. The area outside these circles represents numbers that are neither squares nor cubes. The inclusion-exclusion principle works because it corrects for overlaps. By adding the counts and subtracting the overlap, we get an accurate total. This principle is widely used in mathematics and statistics. If we expand the range beyond 1 million, the method still works. Just adjust the counts based on the square root, cube root, and sixth root of the new upper limit. This makes the approach versatile for any range. Patterns emerge when we look at squares, cubes, and sixth powers. These patterns help us predict counts and understand relationships between numbers. Recognizing patterns is a key skill in mathematics. Solving this problem involves logical steps: define the types of numbers, count each type, identify overlaps, and apply inclusion-exclusion. Following these steps ensures a clear and accurate solution. Efficiency is important in problem solving. By using mathematical reasoning and logical steps, we avoid unnecessary calculations and reach the answer quickly. This approach is valuable in many fields. Roots are central to our calculation. The square root, cube root, and sixth root determine how many squares, cubes, and sixth powers exist in our range. Understanding roots helps us count efficiently. Careful calculation and logical reasoning help us avoid errors. By checking each step and understanding the principles, we ensure our answer is correct. This attention to detail is important in mathematics. In real-world scenarios, counting specific types of numbers is common. For example, in coding, you might need to exclude certain values from a data set. The method we used is practical and efficient for these tasks. A summary table can help organize our counts. List the number of squares, cubes, sixth powers, and the final count of numbers that are neither. This makes the calculation clear and easy to follow. You can explore further by changing the range or the types of powers. Try counting numbers that are neither squares, cubes, nor fourth powers in a different range. The principle remains the same. Curiosity drives mathematical discovery. Asking questions like this helps us learn new methods and deepen our understanding. Keep exploring and asking questions to grow your mathematical skills. Let's review the key concepts: perfect squares, perfect cubes, sixth powers, and the principle of inclusion-exclusion. Understanding these concepts is essential for solving counting problems efficiently. The logical flow of our solution starts with definitions, moves to counting, identifies overlaps, and applies inclusion-exclusion. This structured approach ensures clarity and accuracy. Mathematical tools like roots and inclusion-exclusion are powerful for solving counting problems. By mastering these tools, you can tackle a wide range of mathematical challenges. Efficient solutions save time and effort. By using logical reasoning and mathematical tools, we can solve complex problems quickly. This efficiency is valuable in both academic and practical settings. Our final calculation shows that 998,910 numbers between 1 and 1 million are neither perfect squares nor perfect cubes. This answer is based on careful counting and logical reasoning. Reflecting on the process helps us appreciate the power of mathematical reasoning. By breaking down the problem and applying logical steps, we found an efficient solution. This approach can be used for many other mathematical challenges. Encourage yourself to explore similar problems. Try changing the range or the types of powers and see how the method adapts. Mathematical exploration leads to deeper understanding and new discoveries. In summary, we explored how to count numbers that are neither perfect squares nor perfect cubes between 1 and 1 million. Using logical reasoning and efficient methods, we found the answer and learned valuable mathematical tools. Keep practicing and exploring to strengthen your skills. For further reading, explore topics like inclusion-exclusion, powers, and mathematical reasoning. These concepts are foundational in mathematics and will help you solve more complex problems in the future. Thank you for joining us on this mathematical journey. We hope you enjoyed learning about squares, cubes, and efficient counting methods. Keep exploring and asking questions to grow your mathematical understanding.